Okay, so today we'll be talking about
Sir, I can't hear you.
there you go. Thank you very much. All right. Great. So today we'll be talking about multivibrators, the triggering types, and the synchronous and asynchronous devices here. Okay. As I said, you need to have that knowledge or that information before we start talking about the latches and flip-flops and devices that have to do with that. So when I'm going to talk about that, you will know the concept of that instead of just listening to the lesson and trying to figure out what the heck he's talking about. All right, so multivibrators, triggering, and synchronous and asynchronous devices. First thing we're going to take care of what is it? What is a multivibrator? Okay, so my style of teaching is, yes, I do read sometimes on what's on the screen. It just helps with the retention of the information here. If there are some people have different opinions on that. Some people think we should read, some people think we should not read. But anyways, you know what? If I post a thing on the screen, and if I start talking about it, you're going to try to read it and you're going to try to listen to what I'm talking about, and you will get none of it. All right. So that's the reason why sometimes I'm reading. Anyways, so a multivibrator is an electronic circuit such as oscillator, timer, latch, or a flip-flop, and that's what we'll be talking about the next lesson. So just keep that in mind here. I am going to turn this presentation into a PDF, and at the end of the class, just give me 5 minutes after we are done, you will have that available for download, okay? Now, a multivibrator implements a variety of simple two-state systems, such as high or low. Okay, so it's a device. And then at the end says it produces an output when triggered. Okay, so now this can be externally triggered or the device can be internally triggered. Okay, there are different types of multivibrators. All right. So what does it mean that it implements a variety of simple two-state systems? Well, that means that there's a box, just consider a box or a device, okay, that has an output, and it has two states, high or low. Okay, and the examples that we have done so far, that we have used some of those devices, there could be what? All those logic gates that we have learned or you have learned before I came in here. It's a device that produces either a high or low output, right? So here's an idea of a multivibrator. Now, a multivibrator could be just a simple logic gate, or it could be a device made out of many logic gates and other circuitry that goes around it. All right. So here is a multivibrator. Okay. It gives you an output of either high or low. Right. So that's the first concept. Here's the idea of a multivibrator. It's a device that gives you an output of high or low. How is it? How it is happening that is actually, or how it is going to give you that output? Then we're going to talk about the different types of multivibrators. Okay. So we're going to talk about three types of multivibrators. One is going to be astable, then monostable, and bistable multivibrator. Yeah. Sometimes when you're going to read, you're going to read about 555 timer, right? And the 555 timer could be wired or made into a circuit with external components into Astable multivibrator. So when you're going to read that literature, you're going to know what they're talking about after we're done with this class here, right? So Astable multivibrator. Remember, it's a box. Usually sometimes we just we consider a device. If I want to give you like a general idea of device, sometimes there's a talk about a box, okay, or a device. That gives you two states, high or low. Okay, so how is it going to give it to you? So this is one of the ways. All right. Astable multivibrator continuously switches from one state to another, and it is internally triggered and does not have any stable state. So that's astable or non-stable, but using the word non-stable would be kind of wrong because then it would be unpredictable, right? But astable means that it doesn't have any idle state. It just continuously switches. As an example, it would be an oscillator. So 555 timer can be wired as an astable multivibrator if you want to make an oscillator out of it, right? Which is basically going to oscillate from high or low, just like that. And you're going to choose different parts or components to wire into that chip or integrated circuit or IC to make it go either faster or slower. So you're going to increase or decrease the frequency. And you can also add different components and different values of the components in order to control the duty cycle of it as well. You can make it generating pulses as well. Right? So what's a pulse? A pulse is a very narrow duty cycle waveform. Okay. It could have frequencies or it could be just a single pulse. Right. So astable multivibrator is internally triggered. It doesn't have any per se. It doesn't have any control signals. You could have a control signal because if you wire up a 555 timer, then you can have a control potentiometer or like a volume control type of thing, right? So you can make it go not a volume control. It's a potentiometer, like a regulator that you can make it go faster or slower. Right? Or you can adjust the duty cycle. But the idea is that it does not have a stable state. So for example, it's not going to stay low all the time. And then based on some sort of a triggering from outside, it is going to change its state based on some control. No, once you turn this thing on, it starts oscillating, right? And it doesn't have a stable state, high or low. It just goes high or low. And the only thing you can control usually would be how fast it goes in the duty cycle. Right? But it's an astable multivibrator. It switches, it oscillates, it switches its state all the time. Okay. So it's a astable multivibrator. It's a box that changes its state from high or low continuously. And it says internally triggered. Well, it is because it has whatever the circuitry is to make that thing out of, that internal circuitry makes that thing oscillate. Okay? So here is an idea of an astable multivibrator. Right? Right. The other one was going to be a monostable. All right. So here's a monostable multivibrator. Right? Also known as half astable multivibrator. We're going to take care of that, what that means. Okay? Well, it does have one state. One of the states is stable. So it does have a state, it does have an idle condition, either high or low. Okay. The other state is an astable or transient. Well, we're going to talk about that. So it idles in one state. The other states are triggered momentarily. Right? A trigger pulse can cause that. So a trigger pulse causes a circuit to enter the unstable state, so change the state from the idling condition to something else, which it would be either if it's idling at low, we can make it go high momentarily, or for whatever amount of time that you choose to. Or if it's sitting high, you can make it go low momentarily, or whatever the time you choose for this thing to go low. After entering the astable state, the circuit will return to the stable state after a set time. And the time can be regulated by some sort of a timer, or the time can be regulated by manually changing the condition of it, right? So example, the easiest thing to imagine, it would be a momentary push button switch. You push the switch and it is on. You release the finger from that switch, it returns to the previous position, right? Or it could be a pulse detector as well. So it could be triggered from outside by whatever signal, and you could change its state. And now it could be generating a pulse, or it could be holding that state as long as you have your finger on that switch, or as long as something is making it hold that state. But as soon as the condition disappears, that thing returns to where it was. Okay? So it's called a monostable or a single stable. It has one stable condition. It does have a one idle condition. Okay? Just like a fluctuation. Fluctuation, I'm not sure at which time you have, Vic, I'm not sure which time you posted that chat. Were you referring to the monostable, or were you referring to the astable multivibrator when you say fluctuation?
So you mean that the state is triggered momentarily, so just like a fluctuation in the circuit?
Fluctuation, yeah, you could really use that word if you really want to, but I would be careful with using that word, because a fluctuation, it could be fluctuation in power, right? If you have the
Right.
power grid, so it could go a little bit lower, and so it could fluctuate, all right, but not necessarily change the state from one decisive or but it's since you use that word, I can plug that in and say that it could smooth out the fluctuations. So, like for example, we could use this as a switch debouncer.
Yeah.
You can debounce a switch, right? So
From
when the
my
press is,
because
yeah.
yes, sir. But from my understanding, it's like when the other state is triggered momentarily, so there's something like a fluctuation in the circuit.
Yeah. So yeah, I could, in that philosophical sense, yes, you can consider that. Yeah.
All
Okay.
right, sir. Thank you, sir.
Cool. All right. So we have taken care of the astable multivibrator, which vibrates all the time. You have no control over it. Well, as soon as you turn it on, it oscillates. Okay. And then we have a monostable multivibrator, which sits at one spot until we tell it to go somewhere else, which would be if we're using digital circuitry, it can either go high or low. So it could be sitting low. We can make it go high for some time. And then once we release that condition, it's going to return to its home, okay, or return to its home. So it can go momentarily high, or it can go momentarily low. And how long does it go for? Then we can control that, okay, externally. Okay. Now, then we have a bistable multivibrator. It does have two stable states. So it could either be triggered, it could either be told to go low and stay there. Okay. Or it could be told to go high and stay there until further instructions. Right? So it is stable in either states, state, okay? Can be flipped from one state to another by an external trigger, such as pulse. Be a pulse, or it could be a level. I should change that there. Right? An example of that would be a flip-flop, which we will be studying next time we see each other. Okay? So It could be told to go high and stay there until something changes, and then go low and stay there. Right? A flip-flop could be as soon as you see a circuit, then stay one way. Right? As soon as you see another pulse, then stay another way. Right? Go another way. Right? So it can idle in both states, as opposed to the monostable vibrator that has a designated kind of like a home position or a stable state to go to stay there at all times until something changes and then momentarily go somewhere. All right, which changes condition. Okay, so here's a bistable multivibrator. Okay, then we're going to be talking about triggering. Okay, so we talked about the multivibrators. Yeah. And then I use the word that go and do something when triggered. Telling whatever the device is, telling it to change its condition based on something is called triggering it. Right? Just like triggering, bow or something, right? So there are different types of triggering based on what we want to accomplish. Okay. Where are we here? Okay, so triggering, or the instructions to change the device's condition, could be high level, low level, positive edge, or negative edge. And then there's that concept of applying the clock, right? But the clock actually works based on either level or edge triggering, and we're going to talk about what that is right now. All right, so let's talk about high level triggering. So here is our device, whatever that is. Right? We're not going to even name that. Let's say it has two inputs and it has two outputs, and notice this device has an output that is supposed to be one state, and it has the output. So first one is, we're going to call it Q, and the other one is Q naught. All right, so whatever this is, that is going to change into the opposite. So that's the idea of this type of a device. All right. Now, high level triggering. Notice that there's a thick line. So here's a signal applied to a control pin of this device here. Okay. Now, the device is going to change its state, or it's going to react when this control signal is high. As long as this control signal is high, then the whole device is active. Which way it is going to be, or how it is going to be active, and how it is going to react, it doesn't matter at this point. Right? But when we have that level high, in this case, applied to the control, and this CLK stands for clock, all right? So this device has two outputs, has two inputs, and it has a clock trigger, okay? So when you apply here's my mouse, when you make that input here high, then the inputs are going to be active, and the outputs, or whatever the box is going to react to what the inputs are telling, and how it's going to react, it depends on the type of device. But we're talking about triggering right now. So what did I write here? The input recognizes the level of the signal applied, in this case, high. When the input reaches level high, then the device will react. And notice I put like a little blue line here that is pointing to this point right here. When you see on the schematic diagram, when you see a device like that, and you see like a clock, so if you see clock, that means it's a control signal usually, right? Unless there's some other control terminals, but then you will have to look at the data sheets or the instructions that have to do with whatever the device is. But this is the control signal here. Now, notice that there is just a line going there and there is nothing, no any other symbols there. So that means when you see something like that, that you're going to talk about a level triggering. Right? When this whatever goes high, then the whole thing is active. Right? Well, from that, we're going to go to from high, we're going to go to low level triggering, which is going to be the same, but something has changed here. Right? I keep pointing that thing with the blue line. There's a low level triggering. Well, the input recognizes the level of the signal applied. Right? So this is the input, this is the control input. When the input reaches level low, then the device will be active. It's going to react, whichever way it's going to react, whatever the type of device is. Right? But this is a low level triggering. And notice we have a little bubble here. So when you see something like that, that means this device is level triggered and it's reacting to a low level. It's acting as a low level. It's going to act to a low level control signal. When that signal is high, no matter what happens to the inputs, these two inputs right here, the outputs are not going to react. Nothing is going to change. So as soon as that control level goes down, so the whole device is triggered low level, then the whole thing is going to become alive. And so sometimes you, depending on the circuitry that you're going to design or troubleshoot or install, you are going to distinguish between these type of things. The first thing about troubleshooting is asking yourself, well, the first thing is check the obvious. Is it plugged in? Is the switch on? Is there cable connected to the switch? Things like that. So check the obvious. And the immediate next question when troubleshooting any kind of thing is, what is it not doing? And when you ask yourself that question, it says, what is it not doing? You're supposed to know what it's supposed to be doing. Okay, and then based on finding, okay, it's supposed to be doing that, but it's not doing this, that, and the other thing. What could cause that problem? Well, then as soon as you see that kind of thing, you will know a little bit more. You will have a little bit more information on how actually is that this device supposed to work. So when you see something like the input like this, and you see the little inversion bubble, okay, the not bubble, that means that this input here is triggered on the level low. Right? So this one here, there's nothing, no any other symbols. That's a level triggering, and it's a high level triggering. Then you have that bubble here, then it's level triggering, and it's active low. Okay. First step of troubleshooting is knowing the order of operations, normal operating paths. Yeah, it's it's pretty much it's what I just said, but inverted, right? What is it not doing? Well, in order to know what's not doing, you're supposed to know what it's what it's supposed to be doing. Okay, and there are different types of troubleshooting. All right, so now we're going to go to edge triggering. See where the thick line of the signal is on the low level signaling or triggering, sorry. Here's that thick line. So the device is going to react to this low level signal. Okay. Now we go to positive edge triggering. Okay. The input recognizes the transition of the signal applied. So here's the input here. And whatever is on the, so this, if this input doesn't see the signal going from low to high, it is not going to react. Okay. So when the input changes from low to high, the device will react. So that is called a positive edge triggering. So here's a waveform. It has a positive edge of the waveform or the pulse, and it continues in one state. But since that, so once it reaches the high level, it stays there, then the device will not react. It's going to be inactive until the next time it sees the signal going up again, right? So when the signal goes up, down here and continues down, nothing's going to happen until it goes up again. Then it's going to take a snapshot of the whatever all the inputs are and make that device react for that moment when it goes from low to high. Sometimes we want to have devices that are triggered in this way, okay? So this is called a positive edge triggering. And if you notice that blue line, there's a little tiny bit of a triangle here. That symbolizes that this input is positive edge triggered. And of course, you might all have guessed it by now. The next thing that we would be talking about is the negative edge triggering. The input recognizes a transition of one signal of the signal applied when the input changes from high to low, and the device will react. So it's the same thing, but now when the signal goes low, from high to low, then whatever is going to happening on these inputs, or whatever this thing is programmed to do, or programmed, it could be hardwire programming, or it could be software programming. Whatever this function of this device is, it's going to kick in and react when the signal goes from high to low. So that is called the negative edge triggering. And the symbol of that is this little triangle symbolizes that this is an edge triggering. And this little symbol here, that little bubble, suggests that it is a negative edge triggering. When you see that little triangle without the bubble here, that means it's a positively edged trigger. So again, level, high level, or level triggering, there's no triangle here, so that there's no edge. That means just a level. And there's no bubble here, which means it's a high level trigger. As long as that control signal, the control terminal, control input stays high, then device is alive and well. Right? Then the negative edge, negative level. See that there we have a bubble here right now, so that means the device is active when the input is, this input here is low. Can't see the triangle. Is it because of the quality of the transmission? Let me just see here if I can zoom in here. Okay, so over here, there's a little bubble, so there's a line going, and there is no triangle here. Okay. So that means it's a level triggering, it's not an edge triggering, and there's a bubble here. That means it's a low level triggering. Okay. Now, let me click onto this here. There we go. Now here's a triangle right here. Here's an input, and here's a triangle here. That suggests that this is an edge triggered device. Now, is there a bubble here or not? Oh, no, there is no bubble. There you go. So that means it's a positive edge trigger. The device will react to the positive side of the waveform. When it changes from low to high, then something is going to happen. Now, let's see the bubble here now. Where am I? I'm here. There we go. Now there's a bubble here, okay? But so what can we tell about this type of triggered input? We see a triangle, so we know immediately that this is not a level triggering, it's an edge triggering. And then the next thing we're going to look at, is there a bubble or not? Oh, there's a bubble. So it's a negative edge triggering. So the device is going to change its condition based on the signal going from high to low. So when you have some sort of an input condition here, and based on that, those inputs here and this input right here, something's going to have to happen on the output. And it's not going to happen until this trigger terminal is going to see a transition from high to low. Then it's going to take a snapshot of whatever the input is, and it's going to produce the output according to the function of the device. Okay. What else do we have? All right. Okay, so I'm just going to go back to the thing here. Now, here's the concept of clock pulse transition. And I'm going to read. So I put that thing, this here, this first part in sort of like a shaded gray, because this is not what applies to this clock pulse condition. This here in the regular print is what we're talking about, but this is a preceder to that one. So, okay, let's just say, in order to enable a device permanently, the enable pin can be designed as level triggered. And I put the permanently in quotes because permanently for the time being, for whatever the time you want. That would be the enable pin. Okay. Then the enable pin can be designed as level triggered. This way, applying the signal to the control inputs will cause the device to react instantaneously or to operate, basically, right? An example is the control board that we have, that you have in your kit, and you're going to use that during your last lab, controlling the motor, right? So this is the L298 motor control driver. It has an enable pin. It has an enable terminal. So once that enable pin has some condition, either high or low, and you can find out what that is. I think it's high. Okay. Then the device is enabled. Okay. And then I said, but sometimes we want the device to take a snapshot of the input or input's state. We don't want this thing to continuously operate. We just want to say, let's say, okay, the inputs are going to change, keep changing. There's going to be signals flashing high, low, and all kinds of inputs. And at some point, you're going to take a snapshot of what the inputs are at that moment. So then you can enable the edge. You can design that input to be edge triggered. So this way, you can just going to take a snapshot of the condition of the inputs, right? So what did I write here? In order to enable the device permanently, the enable pin can be designed as level triggered. Then this way, applying the signal to the control input or inputs will cause the device to react instantaneously. For example, the L298 motor driver controller. Right? But sometimes we want the device to take a snapshot of the input or input state at only, oh, I should get rid of one of the ats, only at a certain instance of time. Okay. The enable pin can be designed, in this case, as edge triggered. Right. Examples. Let's see the examples, the real life examples of that. Well, still shot camera memory. Right. So there's an analyzing element behind the lens of the camera, and you push that little, I don't want to use a trigger button, but you can call that, right? And the memory circuitry of the camera is going to see all bunch of stuff on its inputs, but it's not going to react to it. It's just going to see, okay, ignore it, ignore it. Yeah, I can hear you, but I'm not registering you. Okay, I don't want to remember what you say. But you control that at that moment. When you want, it's going to take a short snapshot of whatever is happening at the analyzing element at that moment. It's going to shoot that right to the memory. Okay? So that would be one of the examples. Okay, motion picture camera scanning circuitry. All right, what did I say here? That would kind of be consistent with the enable that device permanently for some time. All right.
Would a like a motion light, for example, kind of count as that, correct? Because it's not, when you walk past a motion activated light, it triggers for that second that you've walked past it, and then it has a cooldown time.
Yeah,
it has a cooldown time before it'll trigger again, and it's holding a circuit during that cooldown.
So in this case, there's a motion sensor that senses the motion, and usually those are infrared. It senses the infrared energy of a human being or an animal. All right. If you throw in a chair, it's not going to react because it doesn't have that warmth to it. Okay, and then that is going to, so the motion sensors, and it has to do with the lights, or when it comes to alarm systems or the burglary alarms. Okay, whatever the complicated circuitry might be, the output of the device, if it's an analog device, is going to be either open or close. And it could close or open with a relay, or it could open or close electronically. If it's a digital device, it's going to send a signal. But let's just talk about the analog thing. So that is going to send a signal. If it's a relay, then it's going to close the relay or open the relay. Usually it's normally closed, and it's going to open the relay. And then when this motion sensor doesn't see the motion going anymore, it's going to close again. But that signal is sent to the receiving circuitry, and because it's a relay, it's a mechanical switch, so that signal will debounced by whatever the circuitry is there, and then sent to a device that latches that signal on. Because if it's a burglary alarm, then you want to stay. We want this thing to stay. So it's going to apply a pulse to a memory circuit, and that's going to trigger some device, and it's going to make it stay. So that would be a bistable, right? Device. Until it's manually reset because somebody comes over and disarm the system and whatever, right? Or sometimes that time triggered. And then whatever the signal is going to happen. So then here is the receivage of that. Now, when it comes to the motion light, that time when the signal is being sent, a timer is being engaged, and the timer goes level. So it's a level triggering of whatever the circuitry is. There we go. and it's going to, the timer is going to keep that level trigger at certain level for a certain amount of time, and then it's going to go low, and then whatever the circuitry is going to stop reacting and sending the signal to other relays that make the big light turn on. Okay, so there you go. Live examples. Yeah, why didn't I think of that? Now I'm jealous. All right,
it's okay, you can have it.
No, you can have it.
But any of your stuff that's going to be motion activated is going to be a momentary interaction that has a progressive delay after the fact, right? Like you said, like if you walk past a motion sensor, it triggers. Whatever it reacts after the fact is built into the circuit. Like you said, it latches.
Yeah. If it did not have the latching circuitry, then the light will flicker on and off, because the motion sensor sees your infrared energy, and as soon as you step out of it or stop moving, it was going to turn off. So it'll be just flickering on and off, and so then the timer is engaged. Okay, once you see that, turn it on for like 30 seconds or so, right? So there it is. So Let's get back to that slide here. Let's go from the beginning. All right. In order to enable a device permanently, an enable pin can be the enable pin can be designed as level triggered. This way, applying a signal to the control input or inputs will cause the device to react instantaneously, for example, the motor control driver, right? Now, but sometimes we want the device to take a snapshot of whatever input state, then only at certain instance of time, then it could be edge triggered. And we talked about the examples here. What else did I say? Depending on the type of the circuitry used, positive or negative or clock can be applied. Did I have another? Yeah, okay. A clock can be applied, right? So sometimes you want to have a pulse, or sometimes you want to have a clock, depending on how you want the device to be. And what is a clock? A clock usually is, well, it would be a stable multivibrator. Clock goes all the time. It vibrates. It has a frequency. Okay, whatever the other circuitry is, it might use that clock to perform some operations, and then it might ignore the clock, and things like that, right? So, so that's why the clock pulse transition here. The clock, well, it goes from one. So as it will be a stable multivibrator, it would just go from one to zero all the time at certain frequency, and then the circuitry, whatever it is, it could be reacting to usually pulses or edge pulses, because clock. See, here's the thing: if you make the clock, the pulses as narrow as possible, then you can have a faster clock. If you have the pulses that have bigger duty cycle, then you're limited with the frequency of the clock, or how fast you want the clock to operate, by the duty cycle of that clock the waveform versus the frequency. But if you narrow it as much as possible, then you can have a faster clock. Then you can have a faster operating circuitry. You can have faster computers, faster cell phones, whatever uses the digital circuitry. Pretty much all the devices are clocked. Okay, doesn't mean the Star Trek clock that makes you kind of invisible. No, it's the clock that it's the digital clock that goes. That works as a stable multivibrator. Okay. Now, we're going to go to the asynchronous versus synchronous device. All right. So let's just see what I wrote here, and I'm going to explain. Asynchronous, and I didn't put the a or an or whatever, because I just want to concentrate on the word here. So it might not be grammatically correct, but I want to have the technicality taken care of. Right. So asynchronous circuit, a circuit which is not controlled by a designated input or inputs, to which either a pulse or signal level or a clock is applied. It's also known as a clockless circuit or self-timed circuit. So a synchronous device would be a simple gate. That would be the simplest thing that I could think of. Let's say we have the AND gate here. We have two inputs and we have one output. Easy, right? So whatever happens, whatever change happens here on the inputs, they could go 0, 1, 1, 0, 1, 0, 0, 1. That input is going to react immediately. It is not controlled. It's not triggered by anything. So this is an asynchronous device. It's not controlled from outside. As soon as you would add another input, which would be like an enabling input, then you can make it into a synchronous device, right? Because that the operation of the circuit of this device would be controlled by some sort of a control input. So depending on whether it's a level triggered or is it edge triggered, then it would turn that device on or off. Okay, so just the gates that we use, the AND gates that we use during our labs, these would be example of the asynchronous device. Okay. Now, so that's why it's a clockless circuit or self-timed circuit. It's not controlled by anything. Whatever happens on the inputs, that thing just lets through and just relays the information, listens. Somebody says something, I'm going to blab it right here. Okay, so we have some asynchronous people in our society. So you got to be careful with that, unless you want the information to pass through. Okay. All right. So synchronous circuit, as opposed to that, it's a circuit which is controlled by a designated input or inputs to which a pulse, signal level, or clock is applied. See, there's only one it says is not controlled, and the other one says that it is controlled by designated inputs, right? And then when you print those, the PDF version of that, I will read what this one says. Nearly all digital circuits, in particularly all CPUs, which is computer circuits, control processing units, like a microprocessor and whatever based circuits, nearly all the digital circuits are fully synchronous circuits, and a global clock is applied. All right. So that's the how fast the clock is. It can make, I can say this computer is faster or slower. All right. So here's the difference between a asynchronous and a synchronous device. And here is the end of this this class. I want you to understand this concept. Hopefully just after this lesson, you're going to remember what, but I would suggest that download the posted notes and watch this video later on, because I'll post the video here, in order to get this thing into your blood. Okay, get this knowledge into your bloodstream. So when somebody's talking about monostable or astable or bistable multivibrator, you're not going to have to go to the Wikipedia and search for that, or you don't have to go to Google and search for, or YouTube to search for that. Get this thing in your blood, so it's going to make it easier for you to understand other parts. These are the basics of the basics when it happens to when it comes to the digital circuitry. Okay, so that's the end of it, and you're going, I understand you have another class to get ready for. So this for the first time, we didn't go overtime with this. All right. Next time we're going to talk about the latches and the flip-flops. And for now, there's no assignment, which means one of the weeks you're going to have 2 assignments, which I'm going to make them accordingly shorter, or I'll adjust the difficulty or whatever the loads to that. All right. But the assignment, the other assignment, assignment 8, was had pretty much not much to do with what I just said. That's why I turned that assignment off for now. Okay, so you have a breather. You don't have to do assignment at this point. Okay, so that's it for this class. And as I said, next time we're going to talk about latches and flip-flops. All right. Thank you very much, guys, and I will see you when I see you.
Thanks, Joe.
Thank you.
Thank you. Have a great day.